Okay, let's get right into this incredibly crucial explainer about what exactly happens to our electronics when we are finally done with them. We spend so much time talking about the software side of technology, but today we're looking at the physical reality of the hardware lifecycle. We're going to dive into the materials inside these devices, the regulatory frameworks surrounding them, and what engineers literally must design for from day one. But before we look at the crazy global data, I want you to do a quick mental tally. Think about the dead devices sitting in your room alone. Seriously, it's estimated that the average household has dozens of unused electronics just tucked away in closets and desk drawers. You know the ones. That old smartphone with the cracked screen, the tangled charging cables, maybe an obsolete tablet. Imagine the combined raw material value of just the items sitting in your own home. It's so easy to think of these things as worthless junk once they stop powering on, but as we're about to see, that couldn't be further from the truth. So here is our roadmap for today. We're going to break this down into 6 parts. The global e-waste crisis, inside your dead devices, the technical recycling process, extended producer responsibility, moving to a circular economy, and finally, e-waste in Bangladesh. All right, let's start with Section 1, the global e-waste crisis, focusing on the sheer scale and the consequences of it. 62 million tons. That is the amount of e-waste generated globally in the year 2022 alone. This number set a brand new and frankly terrifying record. To put that massive scale into perspective for you, that is literally heavier than the Great Wall of China, generated in a single year. It is just a sheer mountain of discarded hardware, and it's expanding year over year at a pace our current infrastructure simply wasn't built to handle. And here is where you really see the failure in the current system. Out of those 62 million tons, only 17.4% of that e-waste is formally recycled. Think about the math on that for a second. If only 17.4% is officially processed, that means a staggering 51.2 million tons of tech is entirely unaccounted for. The vast majority of it is just dumped, burned, or left rotting in landfills completely outside of any formal recycling channels. And because of that massive gap, we are seeing incredibly severe economic consequences. That failure results in $57 billion, with a B, worth of raw materials utterly lost inside unrecycled e-waste every single year. We are talking about high-value elements here: gold, copper, rare earth elements that were mined, refined, and manufactured at great expense, only to just be thrown into the dirt. But look, it's not just about the lost cash. There are over 800 chemicals inside a standard modern smartphone. Now, while some of those are benign, many of them are highly toxic if they get released into the environment through burning or landfill degradation. So when we dump tech, we aren't just wasting money, we are actively creating massive chemical hazards. Moving on to Section 2, inside your dead devices. Let's look closely at the value, toxicity, and origins of what is actually inside these machines. When we map out the specific dangers to the components we touch every single day, the reality is pretty stark. We aren't just talking about abstract, unpronounceable chemicals. We're dealing with a lead in CRT glass and solder. We're talking about mercury hidden right inside backlights and switches. We're looking at cadmium inside batteries and device coatings, and chromium VI, which is used specifically for corrosion protection. If these devices are improperly broken down, these exact elements leach directly into the soil and the local water tables. Thankfully, this isn't going completely unaddressed. Regulations like RoHS, that's the Restriction of Hazardous Substances Directive, are stepping in to actively restrict these specific toxic elements from being put into new hardware in the very first place. By legally limiting the use of lead, mercury, cadmium, and chromium V in new electrical and electronic equipment, or EEE, we can actually begin to stem the flow of these specific toxins entering the waste stream at the source. It's a huge step. Okay, Section 3, the technical recycling process. Let's trace it from collection all the way to recovered materials. Now, as logistics experts point out, this technical process isn't as simple as just tossing an old phone into a blue bin. It requires local collection logistics, manual dismantling, heavy industrial shredding, magnetic separation, and complex chemical smelting to extract both the valuable and the toxic components. All of that just to process it back down to raw recovered materials that can actually be utilized again. It is a massive multi-tiered logistical undertaking. Which brings us to Section 4, Extended Producer Responsibility, or EPR, and the overall product lifecycle. So, extended producer responsibility, or EPR, is an absolute game changer in hardware design and waste management. You see, traditionally, once a company sold you a device, the responsibility ended right there. Done. EPR completely flips that paradigm. It dictates that the producer is financially and legally responsible for a device from cradle to grave, essentially forcing them to internalize the real cost of end-of-life waste management. This legally ties the original manufacturers to the entire life cycle of the devices they make. Next up, Section 5, moving to a circular economy. Let's look at this new strategy in IT. Look at the stark contrast here. For decades, our hardware strategy has been trapped in a linear model, this chaotic take, make, waste mindset. We mine materials, we build a phone, and we throw it away. To solve this crisis, we have to aggressively abandon that linear path and adopt the structure to circular model. This is the paradigm of design, use, recover, redesign. It forces us to view the end of a product's life not as waste, but as the direct starting point for the next generation of design. And this hierarchy brilliantly structures our action plan, and honestly, it might actually surprise you. It maps our options directly by value. The highest possible value comes from simply reusing the device, then repairing it, refurbishing it, or remanufacturing it. Notice where recycling is? Yeah, it's actually listed as a last resort before the absolute worst outcome of landfilling or burning. The crucial takeaway for us is that while recycling is way better than the landfill, reusing and repairing preserve the highest amount of raw material value and embodied energy. Ultimately, this completely redefines what it means to build technology. The software and process waste we used to focus on so heavily, well, that must now be matched by a serious evolution in hardware design. Engineers hold the key here. They absolutely must design devices for this circular ecosystem from day one. That means devices built specifically for easy repair, easy component recovery, and safe dismantling right from the very moment of inception. Finally, Section 6, E-Waste Management in Bangladesh. Let's ground all of these global concepts by looking specifically at a local focus. When we look at Bangladesh, the scale of the e-waste problem is deeply troubling, much like it is in the rest of the world. But here, understanding the massive role of the informal sector is so vital. We're talking about workers who often use highly unsafe methods, like open-air acid baths and burning, just to extract metals from tech. Navigating the local rules and trying to bring these informal practices into safer, structured systems is an immense challenge. However, it also reveals a powerful truth. IT professionals and engineers in Bangladesh possess incredible, direct power to change this trajectory by championing sustainable design and smarter logistics right in their local communities. So I want to leave you with this provocative thought to ponder as you look at the exact screen you are watching this on right now. When that piece of technology inevitably dies, will it just become another toxic $57 billion piece of that 62 million ton crisis? Or, because of new frameworks and circular engineering, was it actually designed for a second life? The future of our hardware depends entirely on how we answer that. Thanks for joining me on this explainer, and I will catch you in the next one.